In this chapter, let's discuss chemical bonds. In the last chapter, we discussed the atoms. Each atom has a single nucleus. In contrast, a molecule is a system with two or more nuclei. For example, the water molecule has one oxygen nucleus and two hydrogen nuclei. To discuss the quantum mechanics of the molecules, the Born-Oppenheimer approximation is used again. It says, the motions of electrons and nuclei are separated. When considering the motion of electrons, the nuclei are regarded stationary. The simplest system with more than one nuclei is hydrogen molecule ion. It is also known as dihydrogen cation. It has two protons and one electron. We can call the protons proton A and proton B. The electronic Schrödinger equation is shown below. The electronic Hamiltonian contains the kinetic energy of the electron and the potential energy of the electron in the electric field of the two nuclei. RA and RB are the distances from the electron to the proton A and proton B, respectively. From here, for better readability, I will use green color for quantities related to proton A and blue color for quantities related to proton B. The potential energy between the two protons is not included in the electronic Hamiltonian. It will be considered separately later. Unfortunately, this Schrödinger equation does not have an analytical solution. That is, we don't know the exact form of the wave function. To approximate the solution, we can use the linear combination of atomic orbitals. Suppose psi A is the ground state of hydrogen atom A. Then, psi A is the one of the atomic orbitals of atom A. Similarly, psi B is the ground state atomic orbital of hydrogen atom B. Because both atoms are hydrogen atoms, psi A and psi B are exactly known. Now, we can create a linear combination of the psi A and psi B. The coefficients of psi A and psi B are Ca and Cb, respectively. Pay attention, such linear combination is not the solution to the Schrödinger equation. It is just an approximation. Nevertheless, we can still insert this function to the Schrödinger equation, and the Schrödinger equation reads like this. Now we can play with this equation. The following pages includes integral in three-dimensional space. But don't worry. We don't need to calculate any of them. First, multiply the equation by the complex conjugate of psi A from the left. Then, integrate the equation in the whole space. There are four terms in the equation. Note that Ca, Cb, and E are just numbers. So, they are taken out of the integrals. Here, each integral results in a number. We can simplify this equation by some notations. For example, the first integral is called the Coulomb integral. It is denoted by HAA. Similarly, the second integral is called the exchange integral. It is denoted by HAB. The fourth integral is called the overlap integral. It is denoted by SAB. Finally, the atomic orbital itself is normalized. Therefore, the previous equation can be written in such way. We can repeat this process but multiplying the equation by the complex conjugate of psi b from the left, and then integrate the equation in the whole space. Using similar notations of Coulomb integral, exchange integral, overlap integral, and the normalization of wave functions, we get another equation. The two equations can be written in the form of matrix. They are linear equations about Ca and Cb. To have non-zero solution of Ca and Cb, the determinant of the square matrix must be zero. It is called a characteristic equation in mathematics, or secular equation in chemistry. If both orbitals are the 1s orbitals of hydrogen atoms, the secular equation can be further simplified due to the symmetry of the system. The two Coulomb integrals are equal. The two exchange integrals are equal too. Finally, the two overlap integrals are also equal. For simplicity, we can use alpha, beta, and s to replace them. Then, the secular equation reads like this. It is a quadratic equation about energy. This quadratic equation has two solutions. They are denoted by plus and minus signs. Though we did not calculate the integrals, we already have qualitative conclusions. First, E plus is lower than the ground state energy of hydrogen atom. E minus is higher than the ground state energy of hydrogen atom. Second, we insert the energy back to the equations. By doing this, we get the relation between Ca and Cb. If E plus is used, Ca equals Cb. We can call them C plus. If E minus is used, Ca equals minus Cb. We can call Ca C minus. And Cb is minus C minus. To find the values of C plus and C minus, we must use the normalization of wave function. That is, the total probability of finding the electron in the whole space is 1. Note that the probability density is the square of the modulus of the wave function. C plus and C minus are independent of the position. They can be taken out of the integral. There are 4 integrals. 2 of them are the normalizations of atomic orbitals. The other 2 are the overlap integrals. So, we can express C plus minus with overlap integral. The final linear combinations of atomic orbitals are shown below. Psi plus is called the bonding orbital because it reduces the system energy. Psi minus is the antibonding orbital because it increases the system energy. The values of the bonding and antibonding orbitals on xy plane are shown below. In the bonding orbital, the wave function is enhanced between the 2 nuclei. While in the antibonding orbital, the atomic orbitals cancel each other between the 2 nuclei. The probability density distributions of the electron are shown in the figures below. In the bonding orbital, the electron has a higher probability to be between the 2 nuclei. It attracts the nuclei towards the center. With a proper distance between the nuclei, the attraction balances the repulsion between the 2 nuclei, and the system is stabilized. In the antibonding orbital, the electron has higher probability to be at both sides of the nuclei. It attracts the nuclei towards the 2 sides, in addition to the repulsion between the 2 nuclei. The nuclei are dragged away from each other, and the system is destabilized. The wave functions of the bonding orbital and the antibonding orbital depend on the distance between the nuclei. The quantities alpha, beta and S also depend on the distance between the 2 nuclei. As a result, the energies of the orbitals depend on the distance between the 2 nuclei. The total energy is the sum of the electronic energy and the electrostatic energy between the nuclei. The plot of the total energy versus the distance between the nuclei is the energy curve. There is a minimum energy in the energy curve of the bonding orbital. The distance corresponding to the minimum energy is the equilibrium distance. The difference between the minimum energy and an atomic orbital energy is the binding energy. In this figure, I show you the energy curves of the hydrogen molecule ion. When the distance is infinity, the energy is the atomic orbital energy. In the energy curve of the bonding orbital, there is a minimum energy. The equilibrium distance is about 2.5 Bohr radius. And the binding energy is about 0.13 times of the energy of the 1s orbital. However, the experiment gives an equilibrium distance of 1.44 Bohr radius and a binding energy of 0.2 times of the energy of the 1s orbital. It suggests that the linear combination of atomic orbitals is not accurate. Nevertheless, it qualitatively explains the formation of chemical bonds. Chemical bonds are bonding orbitals with electrons in them. They are classified according to their symmetries. A sigma bond is a bond with cylindrical symmetry with respect to the bond axis, which is the axis connecting the 2 nuclei. The z-axis is usually selected so that it is parallel to the bond axis. The s orbital and the pz orbital are cylindrically symmetric with respect to the bond axis. So, the linear combinations of them are still cylindrically symmetric with respect to it. We have already seen the sigma bonds from the linear combination of s orbitals in the hydrogen molecule ion. Here, I show you another example. A sigma bond can be the linear combination of 2,2pz orbitals, but how about the combination of s and pz orbitals? Please think by yourself. We can write the constituent orbitals as the subscripts of the symbols of the orbitals. For example, the sigma bonds made of 2,2pz orbitals are sigma 2pz bonds. Whether a orbital is bonding or antibonding depends on if there is a high probability to find the electron between the nuclei. We can use an asterisk to denote an antibonding orbital. A pi bond is bond with one mirror reflection with respect to a plane containing the bond axis. Recall that a 2px orbital has a mirror reflection with respect to the xz plane. So, the linear combination of two 2px orbitals have a mirror reflection with respect to the xz plane as well. They are the bonding pi 2px orbital and antibonding pi 2px orbital. The situation is the same for 2py orbitals. The 2py orbitals form the bonding pi 2py orbital and antibonding pi 2py orbital. They have mirror reflection with respect to the yz plane.